All right, welcome back to the AI Research Roundup. I am your host, Alex. Today we're looking at a trending paper that's all about efficiency. It's called Diversity-Guided MLP Reduction for Efficient Large Vision Transformers. So the big problem with large vision models is, well, their size. They're incredibly powerful, but very expensive to run. The authors here pinpoint that most of a model's bulk comes from its multi-layer perceptron modules. A multi-layer perceptron is a core part of the network with layers of processing units. Their method, Diversity-Guided MLP Reduction, smartly prunes these modules, essentially removing redundant parts while keeping the remaining ones varied or diverse. This diversity is the key to helping the smaller model recover its original performance with minimal retraining. And for those of you who want to get hands-on, the authors have released the official code for this work on GitHub. It has everything you need to replicate their results, including the Python scripts for the main steps like pruning, distillation, which is where the small model learns from the big one, and the final fine-tuning to really dial in performance. Okay, so this first figure really shows the method in action. Part A on the left gives this simple diagram of this multi-layer perceptron reduction. You see the network before, with a bunch of hidden neurons, and then after, where several have been pruned away. But the real story is the graph in part B. This plots performance against model size. The vertical axis is average zero-shot classification accuracy, which is a tough test where the model identifies things it has never been specifically trained on. The horizontal axis is the model size in billions of parameters. Notice how the pruned models on the left are much smaller, but achieve nearly identical accuracy to their huge original versions on the right. It's a massive reduction in size with almost no performance loss. Alright, so we saw the impressive results in that last graph, and this figure really illustrates the two-stage process behind it. It's a classic teacher-student setup. The big, original model at the top is the teacher, and its parameters are fixed. The smaller, pruned model at the bottom is the student. First, the diversity-guided reduction happens, shrinking that multi-layer perceptron inside the student. Then comes the clever part, knowledge distillation. Both models process the same input image, and the student is trained to match the teacher's output, minimizing what's called a distillation loss. This loss ensures the student learns to behave just like its much larger teacher. So this brings us to the core mechanism. How does the model actually achieve that diversity-guided part of the pruning? This figure illustrates the clever math behind it. Think of each neuron's influence as a vector, like the arrows shown here. The method first picks the most important neuron, which is the one with the largest L2 norm. You can think of the L2 norm as a measure of the neuron's overall strength or magnitude. Then, to ensure diversity, it uses a technique based on the Gram-Schmidt algorithm to adjust all the other neurons, removing any information that overlaps with the one it just selected. This process guarantees that the next neuron chosen will capture the most new information, maximizing the diversity of the final, smaller set. Alright, so after that clever math with the Gram-Schmidt process, the big question is, does it work? This table gives us the hard numbers on zero-shot image classification. It compares the original models to the pruned versions. We're looking at the number of parameters, the computational cost or flops, and of course the final accuracy. Take the EVA-CLIP-E model. It goes from over 4 billion parameters down to just 1.24 billion, and its average accuracy actually ticks up a tiny bit. This massive reduction comes with a 3x speedup, and we see this impressive pattern across all the models listed here. Okay, so beyond just classifying images, how well can these smaller models find images? This table dives into zero-shot retrieval. That's like searching for an image using a text description, or vice versa. The main metric to watch is mean recall on the far right, which is an average of how well the model retrieves the correct item across different tests. And just like we saw before, the pruned models are right there with the originals. For instance, the intern VLC model, even after dropping to half its size, actually has a slightly higher mean recall. This shows the compression is preserving that core understanding of how text and images relate. Alright, so we've seen these models can classify and retrieve images, but this table shows us another important test, using what's called a KNN evaluation protocol on the ImageNet 1K dataset. This method is a way to measure the raw quality of the features the model learns for each image. Basically, how well it groups similar images together in its internal representation without any extra training. And once again, the results are fantastic. The compressed models, like EVA-CLIP-E, see their parameters cut by over 70%, yet their KNN accuracy remains virtually identical to the original massive model. So we've established that this pruning method works really well. But is it the best way to do it? This table answers that exact question by comparing different pruning strategies head-to-head. We're looking at the average zero-shot accuracy for the OpenClip-G and EVA-CLIP-E models. You can see other methods like random pruning, or pruning based just on the L2 norm we talked about earlier. They all cause a noticeable drop in performance. But then, look at the bottom row. Our method, Diversity-Guided MLP Reduction, perfectly matches the original accuracy. This result really drives home the main point. Just keeping the strongest neurons is not enough. Preserving diversity is the key. So to wrap things up, this work on diversity-guided MLP reduction offers a powerful and, frankly, elegant solution. It proves we can dramatically shrink these huge vision models, sometimes by over 70%, without sacrificing their accuracy on a whole range of tasks. The key insight is that it's not just about strength, but about preserving the functional diversity of the network. This is a huge step toward making state-of-the-art vision AI more efficient and accessible. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.